Morning, everyone. My name is Ben Rogers. Welcome to Norwich. I work for Paradigm Trust. I'm Director of Curriculum and Pedagogy, and I also wrote this book on teaching physics. So I want to talk to you today about using visuals in science, something we do naturally, we do all the time, and some visuals are better than others, and there's evidence that shows which type of how you use diagrams makes a difference, how you use images makes a difference in your students' learning. And I'll go over some of that evidence now. So I've broken my talk into 4 chunks and I'm rattling through them. First one on memory, so very quickly how using pictures can improve retention over time. Second one is how you might use images in the classroom to improve retention, how you might use images to solve problems, and finally, how you would use your body as a visual way of explaining ideas and encouraging kids to use their bodies and learners to use their bodies to explain, because it has really quite interesting impact on problem solving and memory retention. So, start with memory. You'll all know this, your Ebbinghaus forgetting curve, 100 and however many years old, 30 odd years old. Ebbinghaus, German psychologist, was memorizing random words in German and found that you could learn them all, your 50 words, and hold them in your memory for a short amount of time and do the quiz. But sometime later, maybe an hour later, with German made-up words, might be 10 minutes later, you'd forgotten a fair number of them. You do a retrieval event, and then you find that, notice this curve looks a bit like a half-life. Well, the half-life is longer. And then the third retrieval event, which might be a quiz, it might be labeled a diagram, it might be whatever it is, you'll remember it even longer. And the idea is that if you do enough of these, it levels off. So something like 3 times 5, the first time you learnt it, it took you didn't remember it. It took you 2 minutes and you'd forgotten it again. Second time took a bit longer to forget. Third time took a bit longer again. And now that you've done all your times tables and you use it and so on, if I say 3 times 5, you say 15, it's there now. It's not going to fade off anymore. So it's interesting for me is this curve, this half-life. Is it always the same thing to start with? Well, no. Some things are just more memorable than others. Some things are more sticky. So if you remember something social or a song, it will have a long half-life before you even start. My daughter's learning periodic table song, and they've however corny it is, they remember it. Human relationships, we remember those. We remember what happened in last week's episode to that kid, that character, between that character, but we don't remember really abstract stuff. So a visual helps, and it can make that forgetting decay take longer. So you have to do fewer retrieval events before it's permanent. And here's some evidence for this. So picture superiority effect. A big group of learners had to remember a list of words, split into 2. One half of the group had to write out the words 3 times each. The other half had to draw a representation of that word. And if you look at the original paper, the pictures are awful, and that doesn't matter. So you might do this on a scrap of paper, you might do it on mini whiteboards. It doesn't have to be beautiful diagrams in books. So if you've got to remember a list that includes the word stigma, draw a fairly chunky stigma, stamen, over. And the evidence shows, the research shows, and this is Fernandez from 2 years ago, that drawing has a massively positive impact on recall, really extending that stickiness of the knowledge. Okay, so you draw on the board, that's great, but actually getting kids to draw and to draw on scraps of paper and on if there's ever a list to anything like that, get them to draw a little picture of it, because it's twice as effective in memory recall. Okay, so that's my first bit on memory. I think the important section coming up now is teaching. We all use images on the board. We all put graphics up, and that's really useful. But they're not all equal, and what you do with them is also not all equal. So, should you explain a visual? I've got my visual on the board. You're looking at it. Should I explain it to you? And the answer is, it depends. If you are an expert, so if you're a physicist and you're comfortable with this sort of diagram, Me explaining over the top, which is this red one, actually decreases the amount you'll be able to retrieve. And that's because you can do it all on your own. My wittering in the background is only going to distract you, and so you retrieve less a day later, a week later. If you are a novice, however, and you don't know what that diagram says, me explaining it is a benefit. Me not explaining it, you're having to work it out for yourself. It's just too much. You're overloading your cognitive, it's overloading your working memory, and you'll retrieve less. If you're an intermediate, luckily, it makes no difference. So what I would suggest is, if you're teaching something new with a diagram, first time through, definitely explain it. Second time through, fade that explanation, and eventually don't explain it at all. So by the end of the unit, just put it up. If you need to explain it to one or two kids, go and explain it to one or two kids. But if you explain it to the whole class, you might think it won't hurt, but it does hurt. And this is by Kaluga, Chandler, and the big John Sweller, as part of his cognitive load, one of his cognitive load papers very early on. Actually, not that early on, but an important thing for his piece of evidence for his cognitive load theory. Next one, you've got your visual on the board. You're standing there, that's you. And should you just go through it verbally? Should you label it? Or should you have a separate text underneath? And this actually will also be this is more like your textbook version, isn't it? Well, if you label it, to the middle one, you'll get a certain amount of retrieval later on, depending on how difficult it is. If you hadn't labeled it, but you talked it through, you get much more retrieval later on. And the separate text is the worst. The reason separate text is the worst is because you're having to do more with your working memory. You're having to remember the text for longer while you work out on the chart where it's referring to, and then back and forwards and back and forwards. So that one's harder work. And harder work's not bad, but it's not useful harder work. So that means you've got less retrieval in a day and a week's time. Labeling isn't actually that much better, but verbal is. Now, it depends what you're going to do now. If you're explaining it and if it's the first time, try not to have words on the board. Use your voice. What I normally do now is I will have two slides, one unlabeled and one labeled, or I'll have an unlabeled one on the board and then get the kids to write it down, because obviously you want them to be able to review it later on when they're revising. And an unlabeled diagram isn't actually much use for revision if they can't remember it. So I would then either put the slides up with the words on for them to copy down, or get them to copy it down into their one themselves. But when you're initially talking through, know as few written words as you can. So Oliver Caviglioni's big influence on this presentation. Really, really great book. I've got the picture. We're going to get it. This book, I can't recommend it highly enough. Really excellent. And one of the big things in this book is about organizing knowledge. So a text compared to a graphic organizer, is there any evidence that says is more effective? Well, I'll come to that. So he lists in here a large number of different graphic organizers. The ones I find most useful for science are the top one, which is sort of grouping, which might be your mammals, your fish. It might be grouping elements, whatever you're doing. we love a category. Comparing is a really useful one for improving retention, and learning scientists have got a lot on this on their website. I'll show you an example of that one in a moment, because I find that really useful. Sequencing, we do sequencing a lot. You can do it in words. First I did this, then I did this, then I did this. It's more effective to use a flow diagram. And particularly like this flow diagram, because it chunks. So you've got your main thing here, which might be, I don't know, you're setting up an experiment. This bit might be set up the equipment, and this might be get the Bunsen burner, set it up, put it on a heat-proof mat, put the tripod, and so on. So that whole chunk goes together into one chunk. It helps the kids, helps the learners block together a set of concepts, and that makes it take up less space in the working memory. And you go on to the next bit and the next bit, and then you analyze your results or whatever. This one here, cause and effect, Ishikuru diagram, I'll also go through in a moment, because I find that one very useful. I've used that during lockdown in particular to help learners structure a piece of writing. In fact, these two, if you're doing a compare and contrast longer piece of writing, this really reduces cognitive load and you get much better writing outcomes. And the same with this one. If there are multiple causes for an event like global warming or something like that, you'll find that by stacking these, using these wishbones, you can get a much better piece of writing. And I'll just show you what they look like. So here's my similar different, and I was doing what's similar about the Earth and the Moon. Now, what I would usually do in a class pre-lockdown would be to get the children to do think, pair, share. So they do it first on their own. They write down things that are just about the Earth. So it's got water on the surface, for example. Things that are similar to both, spherical, both have gravity, and things that are just the Moon, so no atmosphere, say. And you go around and you're looking over shoulders really quickly, a minute, 2 minutes, see how many they can do. Then you tell them to look to the person next to them and share. And while you're doing this, you're picking out, you're going around and identifying if a child, Mary, has said something really interesting here that you think the whole class should see. When you do the share at the end, you say, Mary, that one I put a dot by, could you read that out to us, please? And then could you all put that in your one? So you're actually capturing the really good stuff. So you've got the retrieval practice at the beginning, and you've got some new good stuff going in. But the reason it works is because they're taking knowledge they already have and comparing it and contrasting it to other knowledge they already have, building more links. So I would strongly recommend, if you do use one of these in the classroom, you have your own version with stuff in, because it's incredibly hard to think on the fly. Your working memory is fully loaded, looking around, making sure behaviour is managed, making sure all the kids are sorted, making sure you can answer questions, all of that stuff. Actually thinking of an answer at the same time is really tricky. There you go. So very useful. And if you want to get them to do a piece of writing afterwards, having this in front of them has taken one substantial step out of the process, or scaffolded it, so that, like Rosenshine says, it's break it down. You've got a task of compare and contrast the Moon and the Earth. That on its own, and then you'll start writing, is too much of a job. But if you're getting them to compare and contrast using this, they'll do a much better piece of writing. This Ishikawa diagram, business graphic organizer, originally a Japanese professor, and it works by, you've got a cause here and a little bit of writing explaining it, leading to that, another cause. You might use it in history if you were doing causes of World War One, but you might also do causes of global warming. So here's my one about global warming. You've got deforestation as a cause of global warming because it's a loss of the carbon sink, it leads to global warming. Burning of fossil fuels with CO2 emissions leads to global warming. Melting the ice cap, more heat is absorbed because ice is reflective as sea is absorbed more, so you get more global warming. And then you can get a piece of writing out of that. It almost paragraphs it up for you. Now, I've got an interesting thing here. Had a conversation with a couple of colleagues on Twitter about, if you have them down below, well, pointing doesn't help for you, does it? I hope you can see my mouse. Pointing down below, sometimes learners think these ones are the causes and these ones are against the cause. What's the opposite of cause? A factor against global warming, and of course it's not. So I've done the suggestion was, if you do them all above, they all think it's a positive impact, and compared to this one where you think you've got a negative impact. Now, this raises a really interesting question. All of this research that I've mentioned so far is really specific. When you look at the original paper, the drawings to help memory were of a list of different sort of things. The evidence about presenting a graph, does that also apply about evidence presenting a flow diagram? Does it also count about all these different things? And of course, the researchers doing a piece of research is a big job. They cannot test every single diagram that you're ever going to teach. So you've got to remember that it's a useful piece of evidence, but it doesn't mean it works for your diagram. Also doesn't really mean it works for your class. And some of the evidence is done with young kids, some of it's done with older adults. Typically, a lot of education research is done in the university on, or psychology research is done on undergraduates because they happen to be there on campus. So not the same as your year 7 child. So I propose that we start thinking about how we can test it for ourselves in classes. And this is my one from this week. I wrote a piece of software that puts a web page up, and it's either gives you diagram A or it gives you diagram B and then asks you one question. And you have to read quite carefully, so it takes about 30 seconds to answer one of these questions. Well, the evidence that I got from 80 people was that this one is indeed slightly easier to read than the blue one. There's not much in it. That was about 32 seconds to answer the multiple choice question. This one was about 38 seconds to answer the multiple choice question. So I don't think this one's mission critical. But for example, if you were going to compare pie charts and a graphical way of representing the data, and you've got a pie chart and you've got a bar chart, or you've got a cluttered pie chart with lots of information on and a very elegant one, or if you wanted to compare one slide which has got a lot of information on with one slide that's got not much information on, and you're getting the pupils to answer a couple of comprehension questions about that slide, indicating how much information they're able to take in how quickly, we should be able to learn what works for the type of materials we're using. That's what I'm working on at the moment, and I'm blogging about that on Reading for Learning. So if you're interested, have a look. This piece of research here that I did, I call it research, was really quick, it was really easy. My problem is I did it with teachers on Twitter. What would happen when I do this with my class will be interesting to see. I'm presuming you'll get a different set of results. The good thing about now, if I can list a good thing about now, is that we're doing a lot of work on computers, so it's actually easy to do this sort of thing. Split the half class in half, or split. If you've got an Academy Trust, half the kids use one graphic, half the kids use another graphic. Which ones can answer it fastest and most correctly? And you can see that. And then you just know next year only use the good one. So that's my agenda. That's my manifesto for today. Let's move on to the next thing. Problem solving. If you ask a physicist to solve any problem, unless it's trivial, they usually reach for a piece of paper and an envelope and start scribbling. Just looking around my scribbles, I'm surrounded by scribbles. So what it's doing is reducing the working memory, the load on the working memory, or putting some of it out into the world. So here's a really useful idea by a couple of researchers called Larkin and Simon from 87, so it's old. And they talk about search and inference. So if you give kids a wordy question like this, what they've got to do is do some inference, which means arranging the bits, if you like, in a logical way. So one end of the rope is secured to the floor, while the other end is passed through a pulley. You're having to do that work in your head. If you give the diagram, it's there. So you're having to do that less inference work because you can see it's attached to the floor and over a pulley. The free end of the rope is attached to the 5 Newton weight, where you can see that. Now, so it reduces the cognitive load by having a picture, by reducing the amount of inference you have to do, but it also reduces something they call search. If I want to know what is the weight that's being held, I've got to scan through for 5 newtons, which is there. If I want to know what the weight is 5 newtons, I can go straight to it, and I can go straight to it and back and look at the pulley, look at F, and come back to the tension and back again really fast. Whereas if I'm trying to work out all of that, hold it in my head, it's taking up a big chunk of my working memory. So using a diagram really has a substantial effect on reducing the cognitive load. You can answer harder questions more easily with a diagram. So you really want to be encouraging children to draw their own diagram. If they get this, they should sketch it. So the next thing is, how abstract should your diagram be? Here's a nice abstract diagram. If you know your velocity time graphs, you'll know that's probably a bouncing ball. If you don't, it will take a lot of convincing. Excuse me. So I now use a very concrete drawing to go alongside that. Can you see my ball maps onto there? So the ball is being thrown up in the air. Here, the velocity of the ball is decreased going upwards. Here, it's at the highest point. You can see that. This ball now is on the way down, and you can see that because the ball is on the negative side of the velocity. Ball is going really fast now, downwards, almost about to hit the ground. almost about to hit the ground. This bit here, you can then explain that's when the ball is hitting the ground. I'm going to go for gesture here. Ball hits the ground, plonk, squidges, reforms, and takes off again. That's what's all happening in that section of time. Ball is at the highest point here on the rebound. You'll notice you can talk about the ball came in fast, hit the ground and went off less fast. You can talk about energy stores there if you want. Velocity is 0 at the top. That's always a tricky one to get. Velocity is now decreasing until it's bounced again. And then the final one. It hasn't quite reached the top yet. It'll reach the top down here. Another example, you've got concrete roller coaster. That's all very nice. You might end up going straight into words here or straight into calculations here, which is super abstract. There's a bridging visual that I like. If anyone knows me, know I love a bar model. Here's my bar model. What's nice here is these are your energy stores. You talk about energy stores, that's nice. You've got initially your little cart up here. All of its energy is stored as gravitational potential energy. Fine. You'll notice here that the total amount of energy is the same. And visually, that's really obvious. You can tell it's turned into kinetic energy, and a little bit is thermal. And you've got that. If you say that in words, that's fine, but they've got to hold that in their working memory, and they can't be doing other things with it. That end up becomes less effective as a understanding learning tool. Next one here. The thermal is increasing each time. You can really visualize that. The kinetic energy is reduced, and stopped at the top. It's still moving, but it's not moving as quickly. So there's less in the kinetic energy store, but it's gone up against its gravitational potential. And you can see it's still got all of it there. Finally, down the end, it's whizzing along, going reasonably fast. And the thermal energy, the thermal store, those axles and those wheels are quite warm. So now you're ready to go on and start doing calculations. And onto my final section. My other great book, I was going to wave around in front of you, probably by my bed still, is Barbara Tversky's book about thinking with the body. Brilliant book. I bought it as an audio because I'm on the train quite a lot, and then I bought it as a hardback. So, that's how good it is. Lovely quote here. When thought overflows the mind puts it back in the world. If you're thinking at full capacity, you can't see my hands. This under here. If you see me anyway, the harder the thought is, the more likely you are to put it into the world through your body, whether you're moving. If you're thinking about arrangements of carts on trolleys, on tracks and so on, you'll be using your hands, and that has a number of bonuses, and I'll go through those. It's got a bonus for you to reduce your cognitive load while you're explaining a complicated idea. It's got a benefit for the receiver of that visual information. Seems that we're very good at absorbing that information without even having to think about it, of what our bodies are doing. And it's actually very good for problem solving. When you are on your own in a room solving a hard problem, you will start gesturing. There's video piece of research that shows this, that when you're not communicating with anyone, you still use gesture, and it helps you with your problem solving. So let's go. Your proper researchers love a classification, and here are a number of different classifications of gesture. And it's actually quite useful for you to know. You don't have to know them in great detail, but there are ones that are abstract, so pointing at imaginary objects, representing a motion of an object, metaphors. So these here, they might be energy stores. That's my gesture for an energy store, and it's not. It's an abstract energy store. It's not a real thing. I can't really move it around. But now suddenly I can move my energy store around, or my energy store can shrink, or I can put more energy in it. And that's a metaphoric gesture. You've also got this thing called beats, can be quite useful if you've got to list things. So first do that, then you do that, then you do that. You've got your type of gesture. We do that all the time, but it also helps learners. And the final one here is your sort of emblematic one. So if you're sitting there like that, or hands up, or whatever, it's got a cultural meaning, and that's a learned one. It's still a communication. It's still very useful. So This was maths problem piece of research, Cook, Duffy and Fenn about 7 years ago. They wanted to know if a teacher was using gesture or not using gesture, does it make a difference? So in order to make this a repeatable experiment, they used video. And so they had the same audio or the same talk, but in one, the teacher was gesturing away. That's this red one. And in the other one, the teacher was they're not able to move their arms. And so same script and the two recordings, and 90 kids were shown this one, 90 kids were shown this one. And immediately after they did a post-test, did it make a difference immediately afterwards? I'll show you the results in a moment. Then they did 24-hour wait, and then they tested the kids again. Was there a noticeable difference between those two groups? And then finally, they did the transfer test. Now, transfer is one of our one of our aspirations as teachers. If you teach something, if you're teaching about rivers in the UK, and then someone puts up a river in Africa, can you make that transfer? If you've got a mathematical tool, you're talking about energy loss from a roller coaster, can you talk about energy loss from a train? There's near transfer and there's far transfer. Far transfer is really difficult. Using the same tools in a really different context is really hard. So here are the results. Does teacher gesture improve learning? Post-test 1, which is immediately after, yes, there is a benefit for having used gesture, a clear benefit. Post-test 2, that was 24 hours later. The ones with, you can see the blue ones with speech alone, kids have forgotten more, and you'd expect that. But weirdly, the children could remember more if you'd used gesture 24 hours later than they could at the time. The transfer test, which also happened 24 hours later, you can see a really beneficial bonus for the transfer test. So this was they were shown it and taught it in one context, and a question using the same knowledge. I think it was fairly close transfer. The kids who had just the gesture hadn't been pointed out; it wasn't really obvious. Those children were able to better apply it in a new context. So gesture away, I think, is my response to you there. Another one is getting children to use gestures also has a real impact. And the reason I include this one, the reason I'm interested in this one, is I was watching a maths lesson, it must have been just after Christmas, and we use a lot of Turn to Your Partner Explain. Really useful, really good thing to do. But the children turned to their partner, good as gold, explained it, blah, 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 and none of the kids were using their hands. And I just read this paper and thought, we're missing a trick here. So if you train the children to actually physically move, and we do this in maths a lot, physically move items for your to solve a problem, that's a good thing. But the researchers found that just moving items that weren't there, gesture items, metaphorical items around, had just as good effect, if not more effect. Those were your concrete gestures, the red ones. The yellow dot here is if they're using an abstract gesture, so not physically moving the thing, but just pointing or gesturing that one. The more abstract it was, had a different impact. And that was the training problem. So the kids were taught to solve a problem. And you can see a lot of those error bars overlap. But you come down here, a near transfer problem. So when you change the context, the children had to move the physical objects, really, really struggled. Whereas the children who mentally moved the object with their hands or just pointed were much better. Now, this far transfer problem, where it's a really different context, this was a maths problem. So again, it worked for that particular maths problem. We need to, as teachers, take responsibility for not just solving that hook, line and sinker, but saying it's an interesting idea, it's something we want to know more about. Does it work in my class with my kids? And we need tools to help us do that. The learners who used the abstract gesture were able to do the far transfer much better than either of the other two groups. I think that's really important. And that's the end of my whistle stop tour. This book, brilliant. This is Barbara Tversky's book that I've got, the audiobook and the hardback, and the hardback is, I don't know where it is, I'll put it somewhere safe, full of post-it notes at the moment. My Graphics for Learning book, I got it secondhand. It's got, I'm assuming Oliver used it a lot because I used it for my book. Wave my book around. When I wrote that, however many years ago, Oliver refers to the same ones, and so it's useful to go back to the original papers, because I think it's useful to see what that context, what example did those researchers use, how close. I've abstracted the learning from it, the bar chart, but really was moving items around for a maths equation similar enough to moving metaphorical energy stores about. I don't know. We need to find out. This is brilliant. Barbara Tversky's book's brilliant. And I was going to talk about the style in this presentation, but I won't. So, maybe I will. One thing that's useful, I found, you can possibly see it on here. If you add a grid, Google Sheets and PowerPoint allow you to add a grid into your presentation for when you're designing it, and it doesn't show on the screen, so I've had to fake it and put it in afterwards. But when I design mine, all of my slides have this grid on, and you can adjust the grid. You can have a 3x2 or whatever. It makes the slide much easier for kids to read. All graphic designers use this when they're designing stuff. So if you want to make your slides easier to read, put that grid up and just make sure things align neatly and are shared out neatly. It doesn't take much habit to get good at it, and your slides will look nicer, but more importantly, they'll be easier for the kids to read. I'll stop there. Really keen to hear what you think. I'm going to post these slides on my blog, readingforlearning.org, and I'll tweet about it a little bit. And I hope you have a brilliant day. Welcome to Norwich. Next time, I hope you actually come to Norwich, because it's a lovely city, really nice place to be, and it'll be nice to meet face to face. Take care, look after yourselves, and hope to see you all soon.